Hi, and welcome to Astro Image Processing 101, where we introduce the basic concepts behind processing pictures of the stars. My name is Jeremy Lickness, and I'm the webmaster of Deep Sky Workflows. That's where I post the pictures from my hobby. And today I'm going to talk to you in this video about what's called linear processing. This is after we've stacked all our images but before we've stretched them, and I'm going to explain what that means. So let's jump right into it. In this video, we're going to cover quite a few topics. We're going to talk about what linear means. I'm going to show you a little bit about what we call LRGB or luminance red, green, blue processing and linear fit. I'm going to explain cropping and rotations, talk about background extraction, which is also light pollution and vignetting elimination. We're going to talk about background neutralization, color calibration, noise reduction, deconvolution, and finally stretching the image to get that final result. Before I jump into the difference between linear and nonlinear, I want to explain the histogram because I'm going to explain the other concepts in terms of a histogram, and not everyone understands what it is. So this is a low resolution image. There's 3 colors, and the colors are arranged to spell the word high. Let's go ahead and make 3 copies of the exact same thing, and then remove some of the colors so that each of these blocks only has one of the colors in the block. So that looks like this. We've basically got our background on the left, our foreground on the right, and the highlight colors in the middle. Now let's rearrange this one more time and just stack these similar colors into rows. That is a histogram. A histogram really tells you the frequency of pixels at different intensity levels. And that's the key to understanding linear versus nonlinear. So what is linear? If we take an image that's a raw image that we've imaged of space, the amount of light taken at night for nighttime pictures, and especially at great focal lengths, is very little. And that light comes in, and when we analyze it, you'll notice there's a bar to the very left edge. You can kind of see some white, some blue, some green. And that is what a linear histogram looks like. All of the pixels are in the very low intensity range. Keep in mind the right side of the graph represents very bright pixels. The left side is dim pixels, and then we have different colors. So here in our linear image, everything is down at that low intensity side. Now, if we do something called stretching the image, which we'll talk about a little later, this changes the image to become nonlinear. Nonlinear are images that you're used to working with every day. They're the images that have been stretched so that the distribution of pixels maps a broader area. This makes it easier for the human eye to pick out the color, the detail, and the contrast, and brings it into the visual range. One concept you might hear about is LRGB processing or multi-channel processing. A lot of times images come in and they're in separate what we call channels, and a channel is just a frequency range of light. So the most common channels are luminance, which represents the overall intensity of the image, the red, the green, and the blue, and RGB combined make a full image. And it's not uncommon in workflows to either start with these separate channels or to take an image like this one and separate it into the blue, green, red, and luminance components so that you can work with them independently. And there's several reasons for this. Some things like stars show up in the luminance channel better. Nebula often show up in the red channel better. So separating the channels gives you a little bit more fidelity and control over the process. One of the first steps that I typically take in my linear processing is called linear fit. And what that simply does is it takes each channel and matches them up. Here I've got an image of the Veil Nebula, and for various reasons, it's got a bluish greenish cast to it. And in fact, if we pull up a histogram, we can see that the blue and green channels are farther to the right, so they're much higher intensity than the red channel. If we run linear fit, what linear fit will do is it'll align the channels, and there's several approaches to this. I might pull the intensity of the blue and green down so that they match the red, or I might increase the intensity of the red so it matches the blue and green, or I might average somewhere in the middle. But regardless of the approach, what happens is the image changes to something like this, and if we look at the histogram, we can see it's far more balanced and the channels align. Here's the two images side by side, and you can see that the reddish tint on the left has been subdued on the right and is more balanced, although there's a little bit of a greenish tint, and we'll talk about that in some other steps of processing. Another important step to take early in the process is cropping and rotation. So this is an example of a image that was assembled from several different image panels, and you can clearly see it's got an irregular shape. And if you notice the edges, there's really a lot of noise. That green and sort of rainbow color set of bands are all pieces of noise and artifacts that will just throw off image processing. So what we can do is find an area that is a acceptable area that doesn't have any of the jagged edges and isn't often the blank space where there is no signal, and crop it to that so that we have just the signal pixels or the important pixels to work with moving forward. The next step is commonly known as background extraction or light pollution removal. And this is a step that addresses perhaps vignetting, where you have certain lenses that have different lighting at the corners and edges that sort of creates a circular pattern. And then when you just have noise or light pollution. So this is an image of the Tulip Nebula, and the background has quite a bit of ambient light that is interfering with the quality and the contrast of the image. By identifying the areas of background that are true background and not nebula, certain software can remove or extract that background and address the picture so it looks a lot more balanced and the background is actually dark. So again, flipping between the two, you can see this. Now the way that it does this is it takes the picture and analyzes the areas of the background, which are, there's automated processes or you may have identified them manually. And this is the background image it comes up with, and it subtracts that gradient from the image on the left to get to the image on the right. And this is how the background is extracted. Another step that sometimes people forget to run or fail to do is background neutralization. Now, this is not a goal of removing the background. We've already performed background extraction. But what this does is it neutralizes or ensures the background is uniform. So there could be fluctuations where it's darker and lighter, and it tries to stabilize it, not take it completely black, because there's never a complete lack of signal in images, but it tries to make it uniform. Now, I don't have a before and after image to show because the effect is so subtle. It's tough to see, but it can go a long way to helping your image balance out in later steps of processing. If you recall earlier when we talked about linear fit, I showed an example where a star was linear fit but still had kind of a greenish cast to it, and that's this star. So there's another step called color calibration. What color calibration does is it tries to establish a normalized set of colors in your image. And what do I mean by normalized? Well, it's trying to make stars as white as we know stars are, or orange or red or whatever color that is. And it's also on the extreme taking the background and making the background more of a natural dark background color. There's several approaches to color calibration. One approach uses the image itself to calibrate. You might identify the background and a set of stars, and it'll use that. And there's also an approach called photometric calibration. What photometric color calibration does is it takes information about your image and finds similar images in databases that have already been color calibrated and uses those to sort of map the difference between the two and apply those changes. And what you ultimately get is something like this. So our reddish image went through linear fit and had a little bit of a greenish tone, but once we color calibrated it, it was far more balanced, as you can see from that bottom image. One of the least well understood and probably more intimidating steps is called deconvolution. And this was something that was initially designed to correct a defect in the Hubble lens. When Hubble was launched, a flaw was found in the lens, and of course it wasn't a case where someone could easily go and swap out the lens. So software was developed to programmatically correct for that lens. Well, it turns out that the atmosphere is one large lens, and you may get distortion of your stars from the shape of your camera lens, but you may also get it from turbulence in the air and atmospheric interference. So what deconvolution does is it looks at the stars in your image and comes up with a point spread function that represents the distortion in your image, and then it tries to reverse it to make your stars more round. So in this example, my stars are stretched and flattened, so my point spread function would look like that flattened star, and then that would be used to subtract basically the difference between existing stars and perfectly round to just tighten those stars up a little bit and make them look sharper. I'll have a video where I talk about a script that I built for deconvolution that I go into this with more detail and provide visual examples. So look for that later. At a certain stage, your image has come quite a ways. You've removed what parts of the background you can. You've color calibrated. You've shaped the stars as well as you could. Inevitably, though, pictures have noise. There's sensor noise, there's thermal noise, there's a lot of sources of interference that add noise. This image has a ton of noise. It has chromatic or color-based noise, as well as luminatic or noise related to the relative intensities. And we want to address this noise early on, because if we don't, it will get stretched and that signal will be expanded and more mixed with the signal that we want people to see, and it'll be harder to remove. So before I stretch my images, I like to address the color noise in the image. We'll go ahead and run that routine. And then we've got the luminance channel has quite a bit of noise here. So we'll go ahead and run a routine to address that. And you can see it hasn't eliminated noise, and the goal is never to get rid of noise, because there's always some noise and pictures won't even look natural if they're completely noise free. But we want to reduce it so that we can enhance the visibility and the contrast with the parts of the image that we do want people to see. Finally, after we've reduced the noise, the last step is to stretch the image. This brings the image into the visible part of the spectrum. It expands or stretches the contrast, and there's various approaches, but a common one is called a histogram transformation. If you're using software like Photoshop or GIMP, you might just go into the levels for the colors and manipulate those levels to stretch your image. Once the image is stretched, we're in the final stretch to getting it produced and set out. So we'll deal with the stretched image in part 3.